So in the last class, we tried to learn about this volumetric strain test. So sometime back, our Devnath has asked why I should really learn about all this math and so on, so kind of thing. The way we are heading for fluid mechanics is, if you are really picking up something like realistic fluid mechanics, like gas turbine blades, jet planes or cars, whatever that, the question always lies whether we want to be a repairman or we want to be a designer, engineer. Now a repairman may not really in a position to change significant changes with the design, because all the time what he is acclimatized is, this is the way rocket really looks like, this is the way motor configuration really looks like, and this is the way combustion happens, this is the way thrust happens. Maybe I will pump more amount of fuel, I will get more thrust. This is the way he try to really do that. But an engineer can really bring significant changes to the system. The way how we do is, unless we understand the important mechanisms like what it means, stress, how these forces are acting. If I want to really change this force, how material properties to be changed, or based on the material properties, how these forces will be going to change. How much rotation of the flow really lead to change in thrust. It may not be sometimes necessary that you burn more fuel, you are going to get more thrust. That may not be possible. Why? Because when this fluid really comes out of these nozzles at high speeds, there is something named Reynolds number, which we will see later classes. If it exceeds certain kind of threshold, it start developing into instabilities, acoustic noise, it drains out loss of energy. So that somewhat connected with your fluid material, how it really gets deformed, how it is going to get shocks, how it is going to get compressed, and so on, so kind of factors. So what we are trying to do is, can I really learn step by step building blocks? Once these building blocks are done for a couple of lectures, can I really integrate all these building blocks to apply my conservation principles like mass conservation, momentum conservation, energy conservation? Once I have this kind of basic fundamental laws, can I really apply those principles on any engineering device? That is the way we have started. We began with the lots of applications in the first few lectures, try to really appreciate where exactly we see fluid mechanics. Then we went ahead inside that, how it has originated in the 16th, 17th century, what people have really put effort, how step by step they constructed these building blocks to understand those integrity things. Then by 20th century, how they try to really integrate those things to really make it something like working aeroplanes, flying aeroplanes, or moving missiles, rockets, aerodynamics, and so on. That is the direction what we are moving ahead. And what we are trying to say is, right now we are at the 18th century, where people try to connect stress with strain. And that becomes the basis to go further in terms of any conservation laws. And one of the things what we have tried to learn about is, in the strain, something named volumetric strains we try to understand, our volumetric deformation. In today's lecture, we are going to learn about angular deformation. So the same infinitesimal fluid element, if I am going to take it, coordinate axis is x-axis and y-axis, and the material begins at x and at x plus delta x, and similarly it is at y and it goes to y plus delta y. That kind of rectangular infinitesimal element I have taken. Now I would like to really understand, because of various stresses or whatever, in case if this material is getting angularly deformed. What I mean angularly deformed is, initially we have these 4 points A, B, C, D in the back picture, down A, B, C, D. Over the time, this material really translate in space. So A really goes to A prime, B really goes to B prime, C point goes to C prime, D goes to D prime. But it's not like just a translation, but a kind of rotation of the axis also happened. Instead of having such kind of translation to here, what we have is some amount of deformation also happened. And that's we would like to really quantify. The way how we are quantifying is, because it's fluid mechanics, surfaces are always be subjected to velocities. So this point is subjected to u at a given location x. This point is subjected to u at x plus delta x comma y, continuous functions. And this point is moving in the y direction with a velocity v at x location. And this point is moving with a velocity v at x comma y plus delta y. And this is moving in the horizontal direction with a velocity u at x comma y plus delta y. So what we are trying to do is, we have two field variables, velocity in x direction and velocity in y direction. Based on which x location, which y location, we would like to really write that function maybe at x plus delta x for a given y location, what is the field variable. Similarly, v at a given x plus delta x comma y location, what is the velocity in that direction. Similarly, v at x comma y plus delta y location, how that velocity really changes. This we would like to track it at abstract level. And that's the thing what we are trying to really look at for each of these points. U at x, v at x, u at x plus delta x comma y, v at x plus delta x comma y. Similarly, u at x plus delta x, y plus delta y. Similarly, v at x plus delta x, y plus delta y. Similarly, u at x, y plus delta y. Similarly, v at x, y plus delta y. Once coordinate system is fixed, this is the way they travel in space for a given amount of time delta t. If that is the case, if it is getting deformed into a prime, b prime and c prime, d prime, how much angular deformation happened? Can I really track it? How much angle change to delta alpha? How much angle change to delta beta? Now, if I want to calculate delta alpha, what I have to really do is maybe count from A prime to E prime, how much distance it has really moved. Similarly, count the distance from B prime to E prime, so that I can look at triangle A prime, E prime, B prime, which is A prime, B prime, E prime in the triangle. BE prime is this by A prime, E prime. If I can really measure these distances, in some sense, I am in a position to really know what is the angle made as delta alpha. This is the thing what I would like to really calculate. So for that purpose, first of all, let us look at B prime, E prime. That is this distance. Because B point really moved to that location. So what I am trying to do is, this point, try to move with v at x plus delta x comma y over a time delta t. This is the vertical direction velocity with which the point would like to move. So what I am trying to do is, let us first estimate B goes to B prime. Similarly, A goes to A prime. That means if I know A to A prime vertical distance, I know B prime to E prime vertical distance. So from B to B prime vertical distance minus B to E prime distance, if I can really subtract, I will be in a position to really done with B prime, E prime. Is that clear to everyone? Are there any questions what we are trying to do? Objective is to calculate that angular deformation. To do that, what we are trying to do is, in case if it is shifted from one location to another location along with rotation, can I first estimate how much angular deformation happened? To do that, what we are trying to use is the trigonometric identity tan delta alpha is B prime E prime by A prime E prime I would like to use. And B prime E prime is B goes all the way to B prime minus B to E prime in the vertical direction. All are in vertical direction, we would like to really calculate. That means at B point, it is having V at x plus delta x comma y multiplied by delta t in a time minus the point A having V of X. So if this one goes up, this one also goes by that distance. So this distance same. That means V of XY multiplied by delta T. This is the distance in the vertical direction what this point is making. Similarly, look at A prime to E prime. What I have to do? First, let us look at how far this point B really moved to E prime. So that is U at x plus delta x comma y multiplied by delta t. This is the distance what it has moved. And A point, how far it really moved to this. That is U multiplied by xy comma delta t. And A prime, E prime I want. So this is the distance it has moved. This is the distance it has moved. And there is a leftover distance of delta x. So this is delta x. So the total distance from A prime to E prime is whatever this endpoint moved minus whatever this endpoint moved plus whatever the original distance. When I calculate that, that will be U x plus delta x comma y delta t minus U at xy delta t plus delta x. This is the angle what it has moved. Now use Taylor series expansion. Vx plus delta x is V of x comma y plus del V by del x into delta x plus higher order terms multiplied by delta t minus V at x comma y delta t. So V goes cancels out. What is left over is del V by del x multiplied by del x delta t. So del V by del x multiplied by del x delta t. Similarly, U x plus delta x comma y U at xy delta x, the leftover components, if I do Taylor series expansion, U plus del U by del x multiplied by delta x plus higher order terms multiplied by delta t minus U delta t plus delta x. So U cancels out, del U del x delta t plus delta x left over. So let us go back. Del U del x delta t plus delta x. This is the one left over. That means if I am going to really simplify in terms of taking out delta x common out, del V by del x multiplied by delta t by 1 plus del U by del x delta t. This is the leftover component. What we will end up as angle. For very small deformations, this is the way theory develops. At 17th century, who was so going to develop by Gauss, Euler, and so on, so kind of guys, because you would like to have a theory rather than a mechanistic approach. What they try to do is, if you are applying forces, stresses, and so on, so kind of thing, based on the velocity components, what we are trying to measure, the deformation can be quantified by this particular angle delta alpha. For small angles, delta alpha is equal to del V by del x delta t by 1 plus del U del x multiplied by delta t. Now, as our self-equation in fluid mechanics, if I apply a force, material is not just deforming, but deforming forever. As long as you apply the forces, material start deforming forever. It's something different from your solid mechanics. Something like you take something like a rod, you connect it to a pulley, apply a force, something like take a bar, connect it to a rope and hang a weight, the material start elongating and holds for that distance. It won't flow forever. But fluid mechanics, you keep a plate on that. And this is the fluid internally. Think of a situation. There is a plate. and the fluid is this part. This is the fluid part. And now you apply a rope and hang a weight over rope. Material is continuously going, fluid also continuously get deformed. This is the main difference between a solid mechanics and fluid mechanics. So with the time, when you apply constant forces, stresses on the system, it continuously evolves. So what they decided is, because there is variation with the time, it's not a good idea to really keep the time component still in the picture. Can I really ask myself the rate at which this angular deformation really happens? So for that purpose, what they did was, you are calculating delta alpha. So let us calculate to eliminate time as delta alpha by delta t. The rate at which angular deformation happens for the fluid is limit delta t tends to 0. Calculate delta alpha by delta t, which is proportional to, I'm sorry, wait, let me erase this, which is proportional to limit delta t tends to 0, delta alpha by delta t is equal to limit delta t tends to 0, del v by del x by delta t goes off 1 plus del u by del x multiplied by delta t. When delta t tends to 0, this term is insignificant compared to 1. So this can be approximated as del v by del x. That means the angular deformation, one can really think of how v varies with respect to x. If this is the material, if you are applying v component here, how this v component variation, whether it is large or small, is the one which is going to deform the material in that way. So you think of, there is a book, on one side you have a palm, on the other side another palm. You try to move one of the palm with respect to the other palm. That is what we call del v by del x. The same thing one can ask even in terms of horizontal direction. You take a book in between your palms, move one of the palm with respect to other palm with a velocity. That's what you call shear. Based on how it is moving, one will be in a position to really talk about the shear rate of the system. And that is the way mathematically they try to quantify the angular deformation rate is del v by del x, where v is the vertical velocity component. How that vertical velocity component changes with the space in the crosswise direction like x. The vertical velocity components variation in the horizontal direction is the one which really sets deformation in that angular way. It looks like obvious to us, but in 16th, 17th, 18th centuries, it was not that obvious for them. And for that purpose, they mathematically went ahead, try to quantify it. For example, you might be seeing a fan blade, or maybe there is a rocket, I'm sorry, there is a rocket exhaust happening. Let us consider this is rocket and rocket exhaust is coming and so on, so kind of stuff. And this is stationary rocket. Now you are going to keep something like a probe to sense what kind of strain race it is experiencing. Why we are trying to target about it? What kind of stresses or force it is experiencing. Unless I integrate all over that kind of stuff, I will not be in a position to really sense whether the thrust is good enough for it to move or not. Because you don't do like a mechanistic way. You build something like a rocket, you pump some solid fuel or liquid fuel into that, ignite it. Whether rocket really goes into space or not, that is the final step. It will not be the first step. What you try to do is you hold the rocket, you mount it very fixed, and you burn it. What kind of fluid mechanics really happens? You try to measure those things, integrate it. Is it really getting me enough thrust? Or you put a force balance on the system. Is it really giving me enough force thrust? And is there a connection between the thrust, what I am getting, what kind of fluid mechanics happening outside of that. Can I really improvise this fluid mechanics quantity? That means I need to understand the angular deformation, how it is getting expanded, what kind of stresses exerted on that, and so on, so kind of stuff. One has to really do that. That is the way people usually do it. Rather than straight away take a rocket, fill it with liquid, now you ignite it, whether it will go or it doesn't go. They won't go work in that binary kind of mode. There will be intensive testing with the different parameters, different ways to look at that. When all these things are giving you the same thing, then they will decide that yes, this is working case. Now let us go for the field trial. That is the way a scientist works, and the first way, that is the way mechanics work. Wonderful. So similarly, if we are looking at angular deformation beta dot, we have calculated del alpha. That is because of this vertical kind of thing. And delta beta, I would like to quantify. In the similar way, if I am going to really do, I have to handle with U components. If I do that U components, what I am going to end up is delta beta by delta T is equal to del U by del Y. My suggestion, please work it out to confirm it. Work it out, I'm sorry. Okay. Once we know this angular deformation, the total angular deformation of the system, because this point went to delta alpha, this point went to delta beta. Now, what is this preserving angle? This is the next point of question what people try to really ask. Something like when your forces are acting and so on, I understand that your 90-degree angle, this is 90-degree initial angle, maybe going to change it to some other angle. If that is the case, can I really calculate what is that angle? That angle is initially pi by 2 angle minus pi by 2 minus delta alpha delta beta. That is, this entire angle is 90 degrees minus delta beta delta alpha I have to do. So initial angle is pi by 2 minus pi by 2 minus delta alpha delta beta gives me the rate of shear deformation of a plane. What is initial angle rate or initial angle, and what is the final angle? That subtraction tells me the rate of shear deformation, which is equal to delta alpha delta beta. With the time, if we are going to talk about that, delta alpha dot plus delta beta dot, which we will call del v by del y plus del u by del x for a given plane xy. So when you are taking infinitesimal element, whether it is a ship crawling over these oceans or rocket exhaust or fan blades or gas turbine blades, whatever that, you're trying to do some mechanical action. Because of that, liquid particles are going to gain energy, momentum, and they will be driven out from one location to another location by taking out all your energy, trying to deform the material. They are going to do some work. Whatever the energy you are pumping out of the system, most of that energy goes into the system, into liquid, try to drive it, deform it, do some work on the system. Because of that, heating happens. Whenever you are trying to rub the things, naturally heat will be produced. In the same way, whenever fluid particles are going, deforming, and so on, so kind of stuff, some amount of energy really comes out of the system, and that can be better quantified in terms of these deformation rates. To generalize, not only for one of the plane, because we have taken something like a plane, try to understand that plane. Now I would like to do the same thing for this plane, I would like to do for that plane, so that I can make an enclosure. So if I am going to do for all these planes, what I can really generalize is in terms of a deformation gradient tensor, or basically here strain rate tensor I can really define, which can be quantified as del u by del y plus del v by del x. That if I would like to really generalize, it will be del u j by del xi. Sometime back we have shown del v by del x, opposite thing, plus del u by del y for a given xy plane. Now, if I would like to generalize for different planes, it can be written in terms of a second rate tensor. Again, you will learn these things in your mechanics of solids. The strain rate tensor is given as del u j by del xi plus del u I by del xj for I is equal to 1, 2, 3. And at Gibbs notation, if we are really showing that, this is the reason why we have learned about those tensor indices. This is grad u plus grad u transport. So any of your strain rate tensor can be written in terms of Gibbs indicial notations as del u plus del u transpose. This is strain rate tensor. Somehow your shear is responsible for that. And the individual component grad u we call as velocity gradient tensor. It has very important property in fluid mechanics because we are learning the tools. From there, one can really derive something like angular velocity. There is a keyword named angular velocity that can be mathematically quantified as how much del alpha dot happening with respect to beta dot. The difference in these angles tells you how it is rotating, and that is your del v by del x minus del u by del y. This is the definition. When we are working out the problems, you will have better understanding of that system. But at math level, let us just take it as it is, like the difference in this angular rates tells me how it is getting rotated. Maybe if I am going to write it in terms of Gibbs notation, this angular velocity is half of del cross u component. The curling nature of a velocity field tells you how a system is trying to spin. So typically people try to quantify two elements, a body, whether it is spinning without any angular deformation, that kind of things what we call rigid body rotation. Maybe if it is not spinning, you take a book and try to spin it. That is what we call rigid body rotation, where your delta alpha, delta beta always same. There is no difference. But whenever there is a variation on this axis, delta alpha, delta beta is going to change. That means it might be getting a shear kind of deformation. So typically fluid elements try to have that shear deformation always they experience compared to a rigid body kind of rotation. When we are going to learn about Bartha vortices, big cyclones, and so on, so kind of stuff, we will really come across how people really quantify, simplify based on this deformation, try to calculate where pressure is high, where pressure is low, from where to where the cyclone really migrates from one location to other location. They try to quantify in terms of these elements. So there always be two basic elements like rigid body rotation and fluid element thing. And these two things, one can really connect it in terms of a term named velocity gradient tensor, which I just explained, grad u or del u j by del xi. Already you are comfortable with initial notation, so I'm going it in that way. If something like transpose, I want to really calculate del u transpose is change the indices as del ui by del xj. Now bring your matrix algebra. Any matrix can be decomposed into symmetric parts and anti-symmetric parts. Do you remember that? Cayley-Hamilton theorem. Hello, guys. Am I audible? Not audible?
Yes, sir.
So a matrix can be decomposed into symmetric parts and anti-symmetric parts. The same thing here. You can think of this gradient, velocity gradient tensor, second rank tensor, can be, if I am calling it as second rank tensor as A, can be decomposed into half of A plus A transpose plus half of A minus A transpose. That means half of del U plus del U transpose plus half of del U minus del U transpose. And the symmetric part, what we call as strain rate tensor. The more proper definition is symmetric part of this velocity gradient tensor is called strain rate tensor. Skew symmetric part of that velocity gradient tensor is called angular velocity. Though the meaning, this angular velocity looks like supposed to come out of like a tensor of rank 2, but it naturally turns out to be a vector. Because of the subtraction components, the rest of the components become zero. Only trace or diagonal elements survives. So basically, your second rank tensor, when you are going to decompose into symmetric, anti-symmetric part, symmetric part still a second rank tensor called strain rate tensor, but anti-symmetric or skew symmetric part converts in some sense to angular velocity with elements only on the diagonal, but rest of the elements become zero, non-diagonal elements. This has very important property when we are going to learn about vortex flows. And we will close this session up to this level. Something like symmetric part of the strain rate tensor and anti-symmetric part of this velocity gradient tensor. So whole basis is you require velocity field, you require gradient tensor. Once you know that, you can decompose into symmetric, anti-symmetric or skew symmetric kind of components. Symmetric parts we call as strain rate tensor, which can be further leads to linear strain rate tensors, angular strain rate tensors. And what about this skew symmetric part? We will call rotation rate. If these definitions are clear, then the actual fluid mechanics really comes into picture, like what it means vorticity, what it means vortex flows, what it means turbulent flows, and so on, so kind of stuff. It's not about just business or management terms, but one can quantify in terms of math to show that whether this is important, that is important, this kind of process happens, that kind of process happens, and so on. So we will see it in the next class. But just before closing this session, let me ask you a simple question. Are you already